Speaking of contaminants, let's take a look at filtration. As you're no doubt aware, everyday environmental air is chock full of a shitstorm of dirt, dust, debris, boogers, and bug parts that don't belong in pneumatic systems characterized by dynamic seals with close tolerances. Pneumatic filters, similar to hydraulic filters, are made out of closely spaced mesh material designed to exclude certain size contaminants. Clean air, free from contaminants, is necessary for the smooth, leak-free operation of valves, actuators, and other pneumatic components. As a frontline defense, dirty environmental air is first passed through an inlet filter, schematically illustrated as a diamond with a dashed line. The inlet filter performs initial coarse filtration of environmental air bound for the compressor. Here's an example of paired coarse inlet filters on a more industrial scale compressor. While we're looking at this picture, we can see the receiver, the motor prime mover, a double two-stage reciprocating piston-style compressor, the pressure switch, the dump or drain valve, and if you look at the stem of the pressure switch, one of several safety pressure relief valves. Finer filtration occurs later in another crucial component known as a filter separator, ordinarily installed between the receiver and the regulator. The filter portion of a filter separator is schematically symbolized as a diamond with a dashed line. The fine mesh of a filter physically excludes airborne contaminants that pass through the coarser inlet filter into the receiver prior to entering the pneumatic circuit. The separator portion of a filter separator is the triangle and the drain on the bottom. As air is drawn in from the receiver and directed through the filter separator, it does a rapid, almost 180-degree bend as it enters, flinging any heavier contaminants and moisture to the bottom of the bowl. A manual drain on the bottom of a filter separator bowl allows any accumulated moisture and debris to be removed during periodic maintenance. If a filter separator has an automatic drain, it will often include another triangle in the schematic symbol. Here's an example of an integrated filter separator, relieving regulator, and pressure gauge installed right on a receiver. Filter separator on the bottom, relieving regulator and pressure gauge on top. I should note, you might find the motor, compressor, and receiver locked in another room or a soundproof box, the noisy beasts that they are, and an integrated regulator and pressure gauge at air drops placed around a shop or factory at the point of use. While we're on the topic of filter separators and relieving regulators, another component you may see in close proximity is a lubricator. A lubricator is schematically illustrated as a diamond-shaped device with a vertical line hanging off the top. A lubricator is a device that periodically apportions a small squirt or fine mist of oil to compressed air entering a pneumatic circuit. You'll note hydraulic systems have no need for lubricators since the fluid of choice, oil, is itself self-lubricating. Air does not have this inherent property. However, pneumatic systems still need lubrication, and the regular controlled introduction of oil into the airstream ensures the dynamic seals between moving actuators and valves remain functional. I should note, some systems lacking lubricators may necessitate technicians performing regular maintenance to periodically manually lubricate individual components to ensure their reliable operation. Since filter separators, relieving regulators, pressure gauges, and lubricators are often found in close proximity to one another, sometimes integrated and sold as a single device, as in this picture, certain manufacturers may consolidate all of these components into a single simplified schematic symbol that looks like this. The filter is the dashed line. The adjustable relieving regulator is the slanting line. The gauge is the dial. And the lubricator is the vertical hanging line. Using a simplified symbol like this really cuts down on the busywork. One might hear a filter regulator lubricator referred to using the abbreviation FRL, as in show the FNG how to lock out the system and replace the FRL. Let's introduce some other accessory valves and components you might or might not encounter in a larger pneumatic system. Oftentimes a check valve is installed between the compressor and the receiver, oriented such that free flow occurs from the compressor to the receiver, whereas the reverse passage from receiver to compressor is blocked. This prevents receiver bleed down when the compressor turns off. You may also find accessory shutoff valves upstream, downstream, or on both sides of an FRL. Consider these two valves on either side of the FRL, one pretty sophisticated, one pretty simple. The more sophisticated valve on the left is a manually actuated two-position valve with a locking detent. meaning when actuated into one position, the valve stays in that position until an operator makes the conscious decision to shift the valve back to the opposite position, in this case by twisting a manual knob in the opposite direction. The bottom position of the valve vents the FRL and everything downstream to the atmosphere through an exhaust port, which again may or may not feature a muffler or silencer illustrated on the schematic. In contrast, the top position allows passage from the receiver to the FRL and the pneumatic circuit downstream. The second valve on the right side of the FRL is a simple manual shutoff with no venting mechanism. Depending upon your country of origin, you might see a manufacturer illustrate a manual shutoff valve as the opposing triangles, or as one would a two-position valve, also with a locking detent. In the bottom position, it blocks flow from the FRL to the pneumatic circuit, whereas in the top position, it allows free flow from the FRL to the pneumatic circuit. Additionally, you might see a push-to-fit quick disconnect fitting illustrated at the output of a compressor circuit. When a matching fitting is inserted into the quick disconnect, it pushes the poppet off the seat and allows flow from the FRL to the circuit. Additionally, rather than a single quick disconnect fitting, you might encounter a manifold with several quick disconnects, illustrated as a collection of push-to-fit check valves. Lastly, you may see other air preparation elements, like aftercoolers and dryers. As we'll learn in later lectures in the combined gas law, the act of compression increases the pressure and decreases the volume of the incoming air. As a result, the temperature increases, as does the moisture carrying capacity of the compressed air. To counter these effects, you may see accessory components like aftercoolers and dryers, should the larger system warrant their inclusion. An aftercooler is a heat exchanger, schematically illustrated as a diamond with arrows pointing away from the air passing through the center, indicating heat is being pulled out. You recall, this is essentially the opposite of a heater, commonly found in hydraulic systems intended for cold weather operations. Heaters are schematically illustrated as diamonds with arrows pointing into the oil passing through the center, indicating heat is being added to it. Aftercoolers found in pneumatic systems, in contrast, remove heat, thus the arrows point away. If an aftercooler features an air or liquid heat transfer fluid, or HTF, the HTF should travel counter to the airflow. This counterflow arrangement ensures that a continual temperature gradient occurs the length of the aftercooler tube and shell heat exchanger, where the air to be cooled travels in the center, and the HTF is jacketed around the outside, flowing the other way. The cooled air leaving the aftercooler heat exchanger is still warmer than the fresh HTF entering. Similarly, the warmed HTF leaving the aftercooler heat exchanger is still cooler than the hot air entering. Thus, heat is continually extracted the length of the heat exchanger. Here's an example of a simpler radiator-style aftercooler mounted on the back of the small-scale industrial compressor we looked at earlier. Despite the title, the purpose of an aftercooler is not necessarily to cool the air, but rather condense water out of it, as cooler air doesn't hold as much water. Again, we'll examine these properties in further detail in later lectures in the combined gas law. Speaking of removing water, one may also encounter a dryer, of which there are two main types, absorption or desiccant, and refrigerant or chiller type dryers, both of which are schematically illustrated as a diamond with two parallel lines. An absorption type dryer passes air through a bed of chemical gel, similar to the desiccant packages you find in boxes that say "do not eat." Absorption style dryers necessitate regular inspection and replacement or rotation of the desiccant material, whereas a refrigerant or chiller style dryer ironically operate kind of like an aftercooler, only uses a somewhat more complicated refrigeration cycle to chill and thus dry the air. Alright, since I threw a lot of components at you in a short amount of time, let's do a quick knowledge check of the previous material. Pause the lecture and see if you can identify the following components on this schematic, as well as describe their general function and area of responsibility. Aftercooler, check valve, compressor, dryer, dump or drain valve, filter separator, inlet filter, lubricator, motor prime mover, safety pressure relief valve, pressure gauge, of which there are two, pressure switch, receiver or tank, the relieving or venting regulator, and the shutoff valves, of which again there are two. Additionally, see if you can draw the simplified symbol of a consolidated FRL, filter, regulator, lubricator. By all means, pause the lecture and try this yourself. If you're tracking, you should have observed the following. If we travel upstream to downstream, we start with the inlet filter, which performs initial coarse filtration of environmental air coming into the compressor. It's a much coarser filter than the FRL further downstream and serves as a frontline defense to exclude the really big junk floating around the environment. Next, we encounter the motor prime mover that converts electrical power to mechanical power used to drive the compressor. The motor starts and stops at the direction of the pressure switch. The compressor converts the mechanical power of the motor to pneumatic power in the form of pressurized air with a given flow rate. Along the way, we encounter an aftercooler and a dryer with the intention of drying the compressed air prior to being stored into the receiver. Pressurized air is forced through a check valve, which operates as a one-way device permitting forward passage from the compressor to the receiver, but blocking reverse passage from the receiver to the compressor. The check valve prevents receiver bleed down when the compressor turns off. The compressed air is emptied into a sealed metal housing called the receiver, or tank. The pressure in the receiver is controlled by the pressure switch. This is an electromechanical device that starts and stops the motor-driven compressor based off the receiver pressure. If pressure in the receiver is below the set value, the pressure switch starts the motor. If pressure in the receiver rises above the set value, the pressure switch stops the motor. If pressure in the receiver falls below the reset value, the pressure switch again starts the motor. In this start-stop style of control, pressure in the receiver stays inside a predictable span. In the event the pressure switch fails to stop the motor or some other equally bad high pressure event, the safety pressure relief valve would open and vent the tank to atmosphere. Moving further down the line, we encounter a manual dump or drain valve that can be used to vent the reservoir. One might open the dump valve at the end of the day to remove any accumulated moisture, or as part of lockout-tagout procedures to discharge stored hazardous energy in the receiver. Lastly, the receiver itself features a pressure gauge. Given proper operation of this system, we might expect this pressure gauge to oscillate between the set and reset values of the pressure switch. Additionally, this pressure switch lets a technician know if there's any stored hazardous energy in the receiver. Next up, we got the first of two shut-off valves. In the bottom position, the valve on the left blocks the passage from the reservoir to the FRL and vents the FRL and everything upstream to atmosphere. Whereas in the top position, it allows passage from the receiver to the FRL. Immediately downstream, we've got the filter separator, which serves to remove unwanted contaminants and moisture that passes through the inlet filter. The drain at the bottom is used to remove any accumulated moisture. Next, there's a relieving or venting regulator. The regulator function is the left to right pointing arrow. Below the set value, the regulator allows passage from the reservoir to the pneumatic circuit. Above the set value, the regulator closes and blocks passage from the reservoir to the pneumatic circuit. The relieving function, in contrast, is the right to left pointing arrow. If some back pressure in the pneumatic circuit rises above the set value, the relieving function vents this pressure spike back to atmosphere, typically through a muffler, which may or may not be illustrated in the schematic diagram. Between the relieving regulator and the lubricator, we've got another pressure gauge measuring pressure in the pneumatic circuit. Given proper operation of this system, we might expect this pressure gauge to oscillate between the set and reset values of the relieving regulator. Immediately downstream, we've got a lubricator that introduces a controlled amount of oil to the filtered pressurized air. This oil serves to lubricate valves, actuators, and accessory components in the pneumatic circuit. Lastly, we've got a simple manual shutoff valve which selectively connects or disconnects the FRL with the circuit. Lastly, since the filter, regulator, and lubricators are such good BFFs and go everywhere together, you might see them jammed together in a simplified FRL schematic showing the filter as a dash line, the regulator as a slanting arrow, the pressure gauge as a dial, and the lubricator as a vertical hanging line. This consolidated schematic sure beats having dragged this cumbersome herd of beasts around all day. Speaking of consolidation, since compressor circuits can get a little busy, you might see some manufacturers wishing to concentrate on the business end of the pneumatic circuit, like the valves, actuators, and accessory components that actually do the work, illustrate the entire air source and preparation elements as a simple empty triangle pointing into the circuit of interest. Using this shorthand, the business end isn't unnecessarily cluttered. The full compressor circuit might be schematically illustrated in more detail on an accessory page. This being said, while we've got this complete compressor circuit diagram right in front of us, let's discuss a couple of basic troubleshooting scenarios before we call it a day. Think about the consequences of a tiny leak in the reservoir, a dump valve mistakenly left open, or a safety pressure relief valve that after experiencing an excess pressure event and venting it to atmosphere fails to reseat itself properly. Given the receiver is a source of pneumatic energy with leaks in it, most likely the compressor will experience excess runtime because a leak would continually bleed off pressure inside the receiver. As such, pressure in the receiver only briefly or may never rise to the pressure switch's set point, and the motor remains energized and the compressor keeps running and running, all the while the tank keeps leaking and leaking. Excess runtime per compressor might be caused by a leak in one or more of these components or a circuit. Opposite scenario. What happens if the pressure switch fails to open at the set value or is improperly wired to the motor control circuit such that it never turns the motor off? In this case, the compressor would keep running and running and running. Luckily, we have a safety pressure relief valve. Experiencing pressure above and beyond the set value of the pressure switch and approaching design limits of the receiver, the safety pressure relief valve vents to atmosphere, often with a startling burst of noise. Additionally, consider simple operator error. What if the shutoff valve on the left of the FRL was mistakenly placed in the bottom position during normal operation? Would actuators in the circuit work as intended? Absolutely not. Placing this valve in the bottom position prevents passage from left to right and vents everything upstream to atmosphere. Both valves must allow passage from the receiver to the FRL and from the FRL to the circuit for the circuit to run. Lastly, consider erroneous system setup. Let's say a pneumatic circuit necessitates 100 psi at minimum to function properly, and a regulator is moved into a position that ordinarily allows 100 psi. However, unbeknownst to the day shift, the night shift operator in the midst of a goofball binge dropped the pressure switch's set point to half that at 50 psi, or worse yet, turned the motor-driven compressor off. What happens? I'll tell you what happens. Most likely the circuit will work as intended for a couple strokes as the reservoir's stored pneumatic energy is bled down and down. However, it's not going to recharge as intended since the pressure switch's set value has been erroneously adjusted too low. Over time, valves and actuators in this circuit will experience less and less pressure and resultant force as the pneumatic energy stored in the receiver eventually exhausts itself, with the period of time being dependent upon the size of the reservoir and the quantity of stored pneumatic energy in it. The point being, a regulator only regulates downwards. The pressure switch's set point is ordinarily higher than the regulators, such that the regulator allows for brief sips of the greater stored energy in the receiver, thereby keeping pressure inside the pneumatic circuit inside a given range. This is why there are often two pressure gauges within a compressor circuit as illustrated in this diagram, one in the receiver and one in the FRL. Additionally, these pressure gauges serve to tell a technician if there's any dangerous pressure stored in the system during shutdown or lockout procedures. One may also include additional pressure gauges further downstream in the circuit, measuring pressure at the point of use. We'll examine the business end of pneumatic circuits in later lectures. Lastly, it needs to be said that not all compressor circuits contain all the bells and whistles as indicated in this diagram. Some compressor circuits can be quite simple and others astoundingly complex. Case in point, consider this quadruplex compressor circuit in a soundproof enclosure consisting of not one, but rather 4 separate scroll-style compressors hooked in parallel, driven not by a constant speed motor, but by 4 variable frequency motor drives. In the event a little air is needed, a single compressor can be driven at a low speed. If, however, demand increases, all 4 compressors can be run at top speed to meet the demand. Compressors can additionally rotate duty cycle. Lastly, rather than a simple pressure switch that changes state at a given value, the system makes use of a more advanced analog pressure sensor or pressure transducer, which outputs a voltage or current signal proportional to pressure. This is to suggest that much more awaits in future lectures. Until then, this wraps up this brief introduction to air preparation in pneumatic systems. In conclusion, this lecture performed a brief introduction to air preparation in pneumatic systems. We examined the similarities and differences in fluid flow and pressure management in closed hydraulic and open pneumatic systems. Additionally, we introduced the schematic symbols and discussed the function, construction, and purpose of compressors, dump or drain valves, filter separators, relieving or venting regulators, lubricators, safety pressure relief valves, pressure switches, receivers or tanks, aftercoolers, and dryers. Lastly, we discussed how the pressure switch largely controls pressure in the receiver by stopping and starting the motor-driven compressor, and how the regulator largely controls pressure in the circuit by selectively opening and closing a passage from the receiver to the circuit. Lastly, we discussed a couple quick hypothetical troubleshooting scenarios involving the compressor circuit. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource. Be sure to check out the Big Bad Tech channel for additional resources and updates.